Welcome to Lecture 22. In this lecture, we'll give an overview of Helmholtz theorem, the divergence theorem, Stokes theorem, and the fundamental theorem of line integrals. In this course, in the actual physical lectures, we will not be actually dealing with the fundamental theorem of line integrals, but I've put it here just for sake of completeness. So the material for this lecture comes from Reading Assignment 4, Introduction to Section 4, Part 4, and Section 4.5. And the objectives of this particular teaching module are just to give an overview of the theorems used in the remainder of this reading assignment and the various geometrical and mathematical relationships that you should be able to sort of understand. The concepts and visualization skills are basically what we mean by Helmholtz decomposition theorem. The meaning of the symbol J, a unit pseudoscalar, or J bold, which is unit pseudovector. This came about in the last lecture when we were trying to describe a vector which was pointing in the z-hat direction, even though we were dealing with a 2D problem. And so the only way to deal with that was to define a pseudovector, which is a form of imaginary vector. Then we'll look at the divergence theorem in 3D, and the analog in 2D is called Green's flux theorem, followed by Stokes theorem in 3D, and the analog in 2D is Green's circulation theorem. And then very briefly mention the fundamental theorem for line integrals, and that's for irrotational fields, either 2D and 3D, a source-free field 2D, or specific 3D case, another source-free field. These we have to separate into two, as will be seen shortly. So note, in this course we'll not cover in any detail the fundamental theorem for integrals due to lack of time, and also you're not responsible for this material. All right, as usual, is a sort of a quick summary of the topics that will follow that we'll be talking about. Just a general reminder here that the item here that sort of highlight in like an orange color, this is normally not stated in textbooks, but is actually an extension of the 2D case in terms of how we visualize things in 3D. All right, so let's basically turn back to the last lecture when we were looking at the notion of splitting up a field into two components, one involving a field which has source type behavior, which looks like fields are emanating from a single point, and fields basically which form basically closed loops around some axis of rotation. So these two summed together would give you the total field. And what we're essentially saying that any general vector field can be described as a superposition of these two totally different types of fields. Given it's 2D, means that if we were to represent this in a sort of a 3D form, which is required if we're going to make use of the cross product, then the x component and y component of the field are only functions x and y. And of course the z component does not exist in 2D, hence the z component is set to 0. So if we were to look at the curl and divergence of the circulation component of a field, we found that the divergence would be equal to 0 and the curl would be equal to some function, and that function would take on the particular form here. Again, here it's shown as z hat, but in actual fact it will be shown below. We basically represent this as an imaginary vector or a pseudo vector which happens to be pointing in the direction of the z hat vector. Also, for curl and divergence of the flux component of the field, if we take the divergence of flux component, then actually this results in a scalar function, and that scalar function can be just represented by the sum of the partial derivatives for the x component, y component of the field. In this case, of course, the curl component of a field which is purely of flux form is equal to 0. So as I mentioned, the items marked in yellow, this does not exist in 2D. So we've created a fictitious z-axis so as to be able to apply the curl operator, and the axis of rotation is a pseudovector. Now in geometric algebra, which we just briefly discussed in the last lecture, the term g of x minus dfy z hat would be replaced by dgx minus dfy j bold, where j represents an imaginary unit pseudovector, which is aligned with the fictitious axis. And the differential term here is sort of the scalar that pre-multiplies the pseudovector. It's related to the magnitude of the circulation divided by the area. All right, so now let's look at the 3D case, which is generally the one we're interested in. And so we now introduce a formal definition of Helmholtz decomposition theorem and the actual calculation of the flux component and the circuit component of the vector field. So in a very general sense, any vector field is a superposition of a field which has got pure source type behavior and pure circulation type behavior. And what we're saying is that the field which has pure source type behavior can be expressed in terms of the gradient of some scalar function phi. Now the minus term is here purely by a convention. Now this is typically the way it's written. And then the second term is the curl of some vector field A, and this basically represents the circulation component of the field. We call phi a scalar potential, and we call the A a vector potential. Now the other thing is some nomenclature. F flux, which is the field which is purely of a source type, has pure source type behavior. We call this an irrotational field. In other words, no rotational component, but also it's called a conservative field. And this has partly to do with the fact that this has been borrowed from the physics when we talk about conservative fields. F circulation, typically, which is the circulation component of the field, is called a solenoidal field, and this is one we refer to as a source-free field. This is purely rotation. Now, we perform a little bit of a trick here now. What we do is we take this general expression, which involves the superposition of two fields, and we take the curl of this field and the divergence of the field. And so if we take the curl of the field, then the curl of F would be equal to the curl of minus grad phi, right, plus the curl of an A, right? So if we take the curl of the flux vector, okay, then this term was equal to 0. I mean, we've shown in a vector identity in the last lecture, if you take the curl of the flux component, which is this one, right, then this term is identically equal to 0. On the other hand, if you take the divergence of the circular component of the field, which is one described by the curl of the vector potential A, the divergence of that will also be equal to 0 according to a vector identity, which we described in a previous lecture. So these are generally terms that we can state right off the hand. Now, there's a question that comes up in terms of, well, if given a field, how do I compute F flux and F circ? Well, what we'd like to be able to do is compute phi and compute A. If we know what phi is, then we can compute F flux. If we know what A is, we can compute F circ. Unfortunately, there are an infinite number of ways to select phi and A given a specific field F. The question then becomes, how do we obtain a scalar potential and a vector potential, and under what conditions are the solutions unique? The answer to this is partly provided in section 4.6, but you're not responsible for this. We're just basically stating it up front that there are ways to go about determining what phi and A are. F flux and F circ can be computed, as I mentioned, once phi and A have been computed. All right, again, I mentioned that any scalar multiply of grad phi is still an irrotational field, and the -1 factor is there by convention. All right, so now let's look at a sort of a geometric overview of the different theorems, followed by the actual mathematical expressions. So when we're looking at the divergence theorem, we're looking at two cases. One is the divergence theorem in 3D, and an equivalent to divergence theorem in 2D. For the 3D case, the convention is as follows. We always talk about a closed surface. So the diagram on the right shows a closed surface, and that we can identify differential surface area on that closed surface at each point on the surface. And that differential surface area is the unit vector that's normal to the surface, ds. So this is actually the magnitude of the differential surface area. This vector, by convention, must be pointing outwards from the closed surface that encloses the volume. dV represents the differential volume within this volume enclosed by the surface. In 2D, we're talking about a contour which is enclosing an area. So in this case, basically what we're looking at is the normal to this contour, which is shown here, right? And it's assumed that when we do an actual integration, we're integrating in a counterclockwise direction around the contour. Well, these are things to keep in mind. We're going to be mostly focusing on the divergence theorem in 3D. All right, so what about Stokes' theorems? Stokes' theorem is a little bit different, and so let's illustrate this using two specific cases, the 3D case and the and the 2D case. So the 3D case, basically, I've got a little picture here on the right to depict what is going on. So let's look at the individual items here. First of all is that the orientation vector for a differential area on an open surface. So open basically means that it doesn't bound a volume, it's just an open surface. And it's bounded by a closed contour, and it points in a direction consistent with the right-hand rule. All right, and so here is the contour that you see, this red one. And you see I'm traversing the contour in this case in a counterclockwise direction. I could also go in a clockwise direction if I want, but it's a counterclockwise. So we see that this is an area that's bounded by the contour, which is planar, but we also see that this hemisphere is also bound by the same contour. And so there's actually no limit in terms of the number of possible surfaces that we can generate which are bound by the contour. But the main thing is to realize that the differential surface area associated with a contour is basically by right-hand convention. And so if you take the fingers of your right hand, point them in the direction in which you go around the contour, and the thumb points in the direction of the differential surface area vector. So for the planar case, it would be this arrow, and for the hemispherical case, it would be the arrow that you see here. And of course, it will change its orientation as you move back and forth along the hemispherical surface. So these first 3 points here, or these first 4 points, basically summarize what we've just spoken about. Now in 2D, of course, we have the same problem, is that you still use the right hand, but the thumb points in the direction of the axis of rotation, which also represents a differential surface area. But of course, in 2D, the z-hat direction does not exist, so we just artificially give it a label J, which is a pseudo vector, which happens to be aligned with the z-hat direction. So these are the takeaway messages regarding how to assign directions. That it is what's the relationship between the direction of the tangent vector and the normal to the surface area, this surface area being one that's bound by the contour. Now for line integrals, and we're not going to be dealing with this in class, but just very quickly talk about it. We have basically a source-free field, and we have an irrotational field. And so for the source-free field in 2D, we're looking at just a line segment here. We're following this line segment. And we look to our right when we're basically traversing a closed contour. So this is a differential surface. And so this is, again, convention-wise. You always make sure it's pointing to the right. A rotational field, here it really doesn't matter if it's 2D or 3D, because essentially in 2D we're just looking at following this contour in the 2D plane, whereas here we're following a contour in three-dimensional space. All right, what about Stokes' theorem in mathematical form? This is the 3D case. And so now we basically look at mathematically the relationships, again, making use of the diagrams I just shown earlier. So this is essentially the relationship. It says if you take the vector field, some arbitrary vector field, dot product at every point on this contour with the differential tangent vector, and integrate around that closed contour, that's equivalent to taking the curl of the vector field at each point on a given surface, and here I've shown 2 example surfaces, both bound by the same contour. So it could be the planar surface or hemispherical. If I take the curl of the vector field, dot product with the differential surface, and integrate over that open surface, that's equivalent to taking the vector field, dot product with the tangent vector, and integrating around the contour. Now I could either choose the planar surface, which would be this integral, or I could have chosen the hemispherical surface, which is this one, and I'd end up with exactly the same result. So this gives me a degree of freedom where I can choose an area to my liking, do this calculation, and given that these 2 surfaces both share the same contour, I'd end up with the same answer. So this is something to keep in mind, because when we get to reading assignment 5, we'll be applying this theorem to deal with the solutions to some physical problems. All right, what about the divergence theorem, the mathematical form? Again, we know that we have a closed surface, and we also know that the differential surface area associated with the surface must be pointing outwards from the surface. All right, so here is the mathematical form. What it's essentially saying is that if you take the dot product of the field and the differential surface area vector at each point on this closed surface and integrate that resultant scalar function over the full surface. That's equivalent to taking the divergence of the vector field at each point within the volume bound by the surface and integrating this scalar function over the volume. These two are equivalent to each other. Right, and so just make sure that you realize that there is this difference between the divergence theorem and Stokes theorem. Divergence theorem deals with closed surfaces. Stokes theorem deals with open surfaces. The divergence theorem, it's always a vector pointing outwards from a closed surface, whereas for Stokes theorem, it's a vector that's pointing in a direction consistent with the right-hand rule. So they are very different. Just make sure you remember that. All right, so we can also look at the 2D equivalent of Green's circulation theorem, which we call Green's circulation theorem. That's the 2D Stokes theorem. In this case, we would be dealing with contours and areas. And so here we go, if we're going around the contour in a counterclockwise direction, we take the dot product between the tangent vector and the field. That's equivalent to basically taking this scalar function. These are basically derived from the vector field itself, and then integrating this scalar function over the area enclosed by this contour. This is basically called Green's circulation theorem, or equivalently it's Stokes theorem in 2D. Again, the right-hand rule applies. We can also look at the 2D version of the divergence theorem, which we call Green's flux theorem. So in mathematical form, again, we're traversing a contour in a counterclockwise direction, which means the normal vector points to your right, which means it's pointing outwards from the contour. In 3D, it was pointing outwards from a surface. In 2D, outwards from a closed contour. In this case, we're taking the field vector at each point on this closed contour, dot plotting it with the normal to the contour at that point, and then integrating over the closed contour. That's equivalent to taking the partial of the x component of the vector field plus the partial of the y component of the vector field to this scalar function and integrating over this whole area which is bound by the closed contour, and these two are essentially equivalent to each other. Again, this is Green's flux theorem, which is equivalent to divergence theorem in 2D. All right, so then we have basically the fundamental theorem of line integrals for irrotational fields, and so we have 2 points, and we're going to integrate between A and B. And if it's an irrotational field, then we can basically describe the field as being a gradient of some scalar function. This is something we've shown earlier when we talked about the Helmholtz decomposition theorem. So if we basically substitute F flux into this expression here and integrate between point A and point B, we find out that's equivalent to evaluating the scalar function at point B subtracted from the scalar function evaluated at point A. That's basically this result this is the resultant that you get given the fact that F flux is the gradient of a scalar potential. This is a fundamental theorem for line integrals for a conservative 2D or 3D field. We can also look at it for source-free field in 2D, but in this case we define what we call a stream function. And the stream function takes on the field, which is purely of a rotational form, in terms of stream function would take on this form. So given a stream function, if we take these partial derivatives, we essentially are creating a field which basically has pure circulation characteristics. That means it's source free. In this case, if we take the dot product between this vector and the normal to the contour going from point to point A, this is equivalent to evaluating the stream function of B minus the stream function of A. Okay. All right, and the last one would be the fundamental theorem of surface integrals for source-free 3D fields. So in mathematical form, basically, we'd have a contour, as shown here. But what I've done here is basically I have an upper surface and I have a lower surface. All right, so as far as the circle here, for instance, fcircle.nsds, if I basically were to apply this theorem here, I can basically use Stokes' theorem to convert a field into the curl of a vector field. So this is basically fcirc is the curl of the vector A if we're dealing with a field which is basically source free. I can make this automatic substitution. However, this expression, right, in this form can be converted into a closed contour line integral using Stokes' theorem. So from here to here is basically just applying Stokes' theorem, right? And so this is a fundamental theorem of surface integrals for a source-free 3D field. In 2D, basically, we're dealing with a contour. In this case, we're dealing with a surface. All right. Also, you'll notice here again, it does not depend on the shape. So if this is a surface integral, this is a line integral. So this line integral could have this surface or could have had this surface. Why? Because we're making a comparison to the same contour that we see here. This, by the way, the vector potential A will be investigated in EC221 next semester. All right, so to summarize, let's look at some of the key definitions. Starting with what is a vector. A vector field is comprised of a flux component, which is essentially only a source, in other words, irrotational, and a component F circ, which is source-free, in other words, rotational component. Some nomenclature: vector field which is rotation-free, also called irrotational, is defined as a conservative field. The notion of conservative comes from the physics community, and it's basically fields that have a certain property, namely that they are rotation-free. Secondly, a vector field which is source-free is defined as a source-free or a solenoidal field. A source-free field, which would be represented by F circ, is defined by the vector equation F equals the curl of some vector potential A. And depending on whether or not you look at this as a 2D or 3D problem, again, we're wanting to make use of the machinery of 3D. And so for 2D, we have to make sure we set up vector potential A correctly so that we can still use the cross product. So for 3D, A is just simply a vector field with an X and a Y and a Z component for A. Whereas if you're dealing with a 2D field, then the X and Y component A are 0. And the Z component can only be a function of X and Y. That way we can exploit the curl operator. An irrotational field, that's when F is just a source, and that means F flux, is defined by a vector equation gradient of phi, where phi is a scalar potential. And in 3D, it's basically just a function of X, Y, and Z, and in 2D, it's just a function of X and Y. And then to summarize, the two types of fields: the conservative field, be it 2D and 3D. So that would be a field basically which is rotation free, or a source free field, which basically is source free. It's pure rotation. In 2D, basically we're talking about a contour integral, whereas in 3D we'd be talking about a surface integral. So let's look at each one of these in turn. If we look over here, we notice that when we develop the notion of a line integral between a point A and a point B, and given the fact that if this is a conservative field, then F can be written as scalar multiple of the gradient of a scalar potential, and we're integrating between point A and point B, and so this would end up giving you scalar potential evaluated at B minus scalar potential evaluated at A. Now, we'd like to create a closed contour to see what the impact is. So that means we would be going from A to B, and then basically from B back to A. That would be a closed contour. But because these two sum to equal to 0, that means a closed contour integration would be equal to 0. So this in itself is an indication that we're dealing with a conservative field. If by taking a closed contour integral of f dot TDS you get 0, that means you're dealing with a conservative field. In 2D for source-free field, the only difference between this expression and this expression is, in this case, we're basically looking at the normal to the contour that we're traversing. And we're going again from point A to point B, and then from point B to point A, which means it's a closed contour integration. Again, we're computing a flux. And this basically would involve stream functions. So it'd be stream function evaluated at B minus stream function evaluated at A as a result of this. And so this basically produces a positive contribution, this is a negative, and the sum of the two is equal to 0. Given that these two basically form together a closed contour integral, we can write it in this way, but because the sum is equal to 0, it means a closed contour integration is equal to 0. So in 2D, if we see something of this form, then basically we know that F is source-free. Extending the source-free case to 3D means that we would start with a surface integral, which is a closed surface integral. And this closed surface integral would basically be made up of two open surfaces, S1 and S2. You put these two together, stitch them together. So for example, one could be a planar disk and the other one could be a hemisphere. They share the same common contour at the base, and the sum of these two surface integrals is the closed surface integral. Now with a closed surface integral, the direction of the normal has to be facing outward. All right, so in that case, if we look at this and its source-free field, we know that f of the form curl of A, this dictates that it is a source-free field. So we'd have curl of A substituting for f here, substituting for f here. This is over surface 1, this is over surface 2. But by Stokes' theorem, this open surface integral, surface area integral, can be expressed as a closed contour line integral of this form. And similarly for this surface integral, same thing. The only difference between this one and this one is that the surface area vector for one is pointing up and the other one is pointing down. And that means that the contour integration that we're dealing with for this one and this one will be in the opposite direction. But the integrand here is the same as the integrand here. The only difference is that the direction of integration is the opposite, which means this will produce a positive contribution, this will produce a negative, but they're equal and opposite. If we sum them, that gives you equal to 0. Hence, that means that for a source-free field in 3D, if you take a closed contour integration of the dot product between the field and the differential surface area vector at each point on the closed surface, sum value is essentially equal to 0. All right, so that concludes lecture 22. Thank you for listening.